Last class, or rather the last class that I didn't miss, we started by discussing effective field theory and the point of view of renormalization that was proposed by Wilson, Ken Wilson, and goes under the name of Wilsonian RG flow, or Wilsonian renormalization. So let me just remind you of the basic idea of Wilsonian renormalization. So the idea is that you start with some quantum field theory, which is defined over all energy scales. So up to some so for example, if you're imagining a theory with a cutoff, say if you're studying a condensed matter system and the cutoff is the atomic spacing scale, then you define the theory all the way up to the atomic spacing scale. Or if you're talking about particle physics, you might be defining the standard model, say, all the way up to the Planck scale. Okay? So you start with some theory, defined all the way up to some very high ultraviolet energy scale. But we only want to study this at some lower energy scale. And then the idea is that we integrate out the UV degrees of freedom. And here I mean integrate out in the sense of the path integral. So you divide the path integral into infrared, low energy, and ultraviolet, high energy degrees of freedom. You perform the integral over the high energy degrees of freedom, and you get some effective action that is a function of the infrared degrees of freedom, which depends on a choice of scale. So, for example, if you decide to integrate out all of the ultraviolet degrees of freedom, say those all with energy bigger than some scale m, then the effective action will depend on your choice of that renormalization scale m. Okay. And in particular, it will depend on the choice of that renormalization scale m in a continuous manner. And so we can think of the process by which we integrate out these ultraviolet degrees of freedom as giving us some sort of flow on the space of couplings, or a flow, usually known as a renormalization group flow, on the space of couplings. So, for example, you imagine starting with a quantum field theory defined in the ultraviolet with some values of the couplings, but if you're only interested in performing low energy experiments, studying observables involving large wavelengths or low energy, then you can treat the theory as a theory only defined up to some much lower cutoff scale, which I've called capital M here. And the point is that the coupling constants of the theory with the lower cutoff scale will be different from the coupling constants of the theory with a higher cutoff scale. And as you vary this cutoff scale, the couplings will change. And in particular, relevant couplings, namely those with positive mass dimension, become very important in the infrared. In particular, they grow as you decrease the cutoff scale, whereas irrelevant couplings, those with dimension less than 0, become unimportant in the infrared. And so, in a sense, this explains why, if you're only interested in studying low energy physics, you'll naturally end up with what we call the renormalizable quantum field theory, namely a quantum field theory where you only have relevant couplings turned on. But what I'd like to discuss today is something slightly different. So In this class so far, we've really studied two different kinds of things that we've called renormalization. So for the first month or so of the semester, we studied the process of renormalization where we defined a scale on which we imposed some physical conditions that fix the coupling constants and the wave function renormalization and so forth. And then we observed that when we write everything in terms of those physical couplings, all of the ultraviolet divergences cancel. Okay, so that's one thing that we called renormalization. And we studied in sort of some great detail how you define renormalized perturbation theory, introduce counterterms, and so forth. This is some other thing that I'm calling renormalization. Okay, I'm distinguishing it slightly because I'm calling it Wilsonian renormalization. But the question that you might naturally be asking yourself is, if these two things are both called renormalization, are they essentially the same thing? And are they related in some crucial way? And of course, the answer is yes. And so what I'd like to do today is tell you exactly how it is that we can relate Wilsonian renormalization to the previous discussion of renormalization in terms of, say, renormalized perturbation theory. So, in order to discuss this, what I'd like to start out by doing today is considering a relatively simple example. Okay, one of the simplest possible examples of renormalization, which is a scalar field theory with a phi to the fourth interaction. So I'm going to set the mass squared equals to 0. As we discussed last time, this involves a huge fine-tuning. In particular, if you have a mass scale that is small but non-zero, as defined at some ultraviolet scale, because the mass is a relevant coupling, it's going to get larger and larger and larger as you reduce the renormalization scale. And so if you really want to set the mass squared equals to 0 at some point in the infrared, then that means that you have to make a sort of a huge fine-tuning in the ultraviolet. And let's just go ahead, for the sake of simplicity, just to keep all of our formulas simple today, I'm just going to study this massless phi-4 theory. And by the end of class today, I'll tell you how you also include the effects of a mass term. But for the time being, let's just consider massless phi to the 4 theory. Okay. And so what I'd like to do is just start considering this theory from the point of view of renormalized perturbation theory, counterterms, and so forth, and we'll discover exactly how it is this renormalized perturbation theory relates to this Wilsonian approach to renormalization. Are there any questions before I proceed? Okay. So let's just remember a little bit how renormalized perturbation theory works. Well, if you just start computing naively with a lambda phi to the 4 theory, you'll obtain UV divergences coming from loop integrals. And we remove these UV divergences by rewriting everything in terms of some physical coupling constants. And we do that by enforcing some renormalization conditions, or some physical conditions, at some energy scale, capital M, which is usually called the renormalization scale. And the point is that this renormalization scale that we've introduced here as a place where we impose some physical conditions that we use to define our renormalization conditions to fix the counterterms is really essentially the same as the scale that we introduced when we studied Wilsonian effective theory. And in particular, as we'll see, if you think about the dependence of coupling constants on the renormalization scale, you have the exact same flow in the space of couplings when you think in terms of renormalized perturbation theory as you do in Wilsonian effective theory when you think in terms of integrating out ultraviolet degrees of freedom. So let's just see exactly how that works. And I'll just work this out in a very simple example so that you can see sort of hopefully completely explicitly how this works. Okay. So the renormalization conditions that we impose have to be imposed at some energy scale. So we're considering a massless phi to the 4 theory, so there's no dimensionful parameter in this theory, so we just have to pick some scale that I called capital M, at which we want to impose our physical conditions. So, for example, we would like the 4-point function at this energy scale to be equal to minus I lambda. Okay, this is how we define the physical coupling. So say at the point where P1 plus P2 squared is equal to M squared. Okay. Now, for technical reasons, which are going to become clear a little bit later, what I actually want to do is enforce this at a space-like value of the momentum instead of a time-like value of the momentum. You'll see in a little bit that this will help me keep all of the various quantities and logarithms that I'm going to find real as opposed to imaginary. But the point is that what we want to do is enforce this condition at some space-like value of the momentum that's set by this renormalization scale M. So this is the condition that defines the renormalized coupling lambda. And we also need to enforce the wave function normalization. So in particular, what we need is that the phi self-energy must vanish at p squared equals minus m squared. This is the thing that we called capital sigma. And its first derivative with respect to p squared also must vanish. At p squared equals to minus m squared. And these two conditions are to enforce the fact that your 2-point function has a pole at p squared equals to 0, as opposed to some other value of p squared, and moreover that the residue of that pole is equal to 1. So what we want to do is understand how the physical observables of the theory, namely the correlation functions, will depend on our choice of renormalization scale. So the question is, how do observables depend on the choice of renormalization scale? Now, this all might seem a little bit formal, but just maybe as an advertisement for the utility of this sort of reasoning, by the end of class today, if I move quickly enough, we'll be able to take this question and turn it into actual physical predictions for physical systems. So in particular, this lambda phi to the 4 theory that we're studying actually turns out, once you study the renormalization in detail, to be a very good model for a large class of material systems, including magnets. So, so by the end of class today, and if not today, by next class, we'll be able to use some of these insights about renormalization to actually study real condensed matter systems and do things like predict critical exponents and things like that. So the observables of the theory are things like Green's functions. So I'll just denote by G sub n, say the Green's function of n fields inserted at points x1 up to xn. And I'd like to understand how this depends on renormalization scale. Now phi here is the renormalized field. And so what we want to do is imagine that the Baire field phi naught and the Baire coupling lambda naught are held fixed, while the parameter m is being varied. And then what we want to do is understand how this Green's function varies as the renormalization scale is varied. Well, the dependence of Gn on the renormalization scale then is relatively simple. So in particular, the field phi is related to the Baire field simply by a factor of the wave function renormalization, which is a function of m, because we have to integrate, well, which is a function of m. And so that means that Gn is just given by n powers of this wave function renormalization times the analogous free field correlator of the Baire fields. And so if we want to understand the dependence of the observables on a renormalization scale, then what we really need to do is think about the dependence of this wave function renormalization on the renormalization scale. So in particular, let's just imagine that we have some small variation of the renormalization scale, say where m goes to m plus delta m, then phi will go to phi plus delta phi, where delta phi is, well, how do we want to call it? Well, it's basically the variation of z with respect to m. So typically this is called eta, so we'll call it delta eta times phi, where delta eta just takes into account the fact that the renormalization scale, that this wave function renormalization z is changing. So it's just z evaluated at m plus delta m to the 1/2 over z evaluated at m minus 1. And likewise, as you vary the renormalization scale, the physical value of the coupling is going to change as well. And the point, really, is that Gn is a function only, can be regarded as a function only of the renormalization, the renormalized coupling lambda and the renormalization scale m. So that means that the variation in this endpoint function is, well, it's the derivative of Gn with respect to lambda times delta lambda plus the derivative of Gn with respect to m times delta m. And if we compare that to this expression up here, if we just use this fact, so if you just use the fact that Gn is a correlation function of n fields, and each phi picks up a factor of delta eta times phi, then delta Gn just has to be equal to n times delta eta times Gn. Or if we want to rewrite this equation a little bit, we can just define a parameter beta. So we can divide that whole equation by delta m and define a parameter beta. So in fact, I'll multiply times m over delta m and define a parameter beta, which is m over delta m times delta lambda, and a parameter gamma, which is m over delta m times delta eta. And this condition right here then becomes a differential equation that's obeyed by the by the endpoint function. It says that m times d by dm plus beta times d by d lambda plus n times gamma of the Green's function, or of the endpoint function, is equal to 0. So I haven't actually done anything here. Really, all I've done is express the fact that as we change the renormalization scale m, that change can be, that leads to two different types of changes in the Green's function. So as you change the renormalization scale m, as reflected by that first term, that must be accounted for by some flow in the space of couplings, along with the fact that the fields phi themselves have some wave function renormalization that's accounted for by this parameter that I called gamma. So this equation is known as the Kalin-Symanzik equation. And it both, and typically the way that this is used is as an extremely efficient way of computing the beta functions. Well, let me say that a slightly different way. So this equation tells us how the observables of the theory change as we change the renormalization scale. And so, in particular, one of the things that we'll see is that it provides a nice way of thinking about the beta functions in terms of renormalized perturbation theory. So that's what we're going to do next. Maybe just to make contact, so just to explain a little bit the notation that we're using here, let's just stare at these definitions for a second. So let me rewrite them a little bit. So beta, as given by this definition, could also be written as the derivative of the coupling with respect to the log of the renormalization scale. Because the derivative, because m d by dm is the same as d by d log m. And so this is the derivative of the coupling with respect to the renormalization scale when you hold fixed the bare couplings. And this is, as you can tell by the fact that I've called it beta, the same as the beta function of Wilsonian RG flow. Remember, in Wilsonian RG flow, we actually had the identical formula. It was interpreted a little differently. In Wilsonian RG flow, the beta function was interpreted as the way that the coefficients in the effective action at low energy change when you integrate out the UV degrees of freedom above some scale m. Here, this beta function is defined to be the change in the physical low energy effective coupling as you vary the renormalization scale m. But it turns out to be exactly the same thing. And indeed, what we're going to do next is actually compute this thing using this sort of definition in scalar phi to the fourth theory, and we'll reproduce a result that we derived last class using the effective field theory approach of Wilsonian renormalization. And finally, this function gamma write this down below. So gamma was m over delta m times delta eta, which could be rewritten. So we can then use the fact that delta eta is essentially z to the 1/2 power to rewrite gamma as 1/2 d by d log m of the log of the wave function renormalization. So essentially, this parameter gamma is telling you how it is the wave function renormalization factor that you need to rescale your fields by varies as a function of the renormalization scale. And this is usually referred to as the anomalous dimension of our field phi. In order to understand why this is called the anomalous dimension, it's useful to stare at this final term in the Kalin-Zemanczyk equation. And if you just imagine that the beta function is equal to 0 for a second and look at that final term, remember that there are n insertions of the field phi in this in Gn. And so what this equation is telling us, m d by dm plus n gamma g is equal to 0, it's telling us that as you do change the renormalization scale, this Green's function is just rescaling by an overall factor determined by that constant gamma. And so gamma is really telling you how the n fields scale as you change the renormalization scale. And that's why it's called the anomalous dimension. It's anomalous because well, as we'll see in just a second, it vanishes at leading order in perturbation theory typically, and it's only non-zero at higher orders in perturbation theory. So it's a little bit like a quantum mechanical contribution to the dimension of your field. And we'll make that a bit more precise later on in the class. Any questions so far? So I apologize, this is a little abstract, but we're going to make it much more concrete in just a second. Yes? Yes. Sorry. This equation. This equation?
Yeah, that's right.
Yeah.
I'm not sure I understand why lambda and m are independent variables. Because m depends on m.
Yeah, no, I mean, that's an important point. I mean, the idea is that you can, if you fix lambda naught, then lambda is determined in terms of m. But you can regard this also as a function of lambda. What you can't do is regard this simultaneously as a function of lambda, lambda naught, and m. You can either regard it as a function of m and lambda naught, or as a function of m and lambda. All right? Is that clear more or less? Yeah. Okay. Good. No, that's actually sort of a subtle point. Yeah. I mean, the point really is if you want to think about this in terms of effective field theory, where m is playing the role of your renormalization scale, where you don't care about degrees of freedom above m, then you should think about Gn as being computed in the effective theory where you only have degrees of freedom below the energy scale m. And when you do that, lambda is just the coupling constant of that theory. And so you could imagine computing Gn using the effective theory where you only have field degrees of freedom with momentum below m. You have some coupling constant lambda. It's just some quantum field theory computation where all of your UV integrals are just explicitly cut off at the energy scale capital M. And then you'll get some answer for G as a function of lambda and M. And in fact, that's sort of an important point. So given this way of thinking about it, I think it's clear that the beta and gamma are, in principle, functions of lambda and m. Okay. But they're both dimensionless. Right? So for example, lambda is dimensionless, and so beta, which is m over delta m times delta lambda, is also dimensionless. Likewise, gamma is dimensionless. And the coupling lambda is dimensionless, but m is dimension full. So because beta and gamma are dimensionless, they're both functions only of the coupling lambda. It's a general result. So far I've just written down the Kalin-Zemanzik equation for scalar phi to the fourth theory. But in general, for a theory with many couplings, there's going to be a Kalin-Zemanzik equation which tells you how the various correlation functions change under a change of the renormalization scale. So let's call them, so let's say that we have a Green's function where you have, let's say we have many different types of couplings and many different fields. Let's call them, say, phi 1 up to phi k, labeled by an index j. Then there'll be an anomalous dimension gamma j for every field. And if you want to calculate a Green's function where you have, say, n1 insertions of field phi 1 and up to nk insertions of field phi k, then what you'll have is a beta function for each dimensionless coupling in the theory, and you'll have anomalous dimensions for each field in the correlation function that you're trying to study. So you have one beta function for each dimensionless coupling. And in fact, as we'll see hopefully at the end of class, you can also generalize this, if you think about it carefully, to theories with dimensional couplings as well. So that's the general form of the Kalin-Zemanzik equation. But what I'd like to do is to kind of take this all down to earth a little bit. And I would like to use this formalism to compute beta and lambda for scalar phi 4 theory. In particular, what I'm going to do is I'm going to start, say, by computing the two-point function. And I'll compute it at one loop order, and I'll demand that it satisfy the Kalin-Zemanzik equation. And then from that, I'll be able to read off some properties of beta and the anomalous dimension gamma. I think I call it lambda gamma. any questions before I do so? Is this Callan's, I understand this is all a little bit abstract, but hopefully if I do an explicit calculation, it'll, bring it down to earth a little bit. Any questions before I continue? Oh yes, do you want to take an intermission? Sure, we're taking an intermission. How do we do this? Oh, okay, so let's continue. So what I'd like to do now is use this Callan-Zemanzik equation to compute the beta functions of scalar phi 4 theory. Okay, so how does this work? Well, let's first think about the two-point function. Okay. So the two-point function, working in perturbation theory, is given by the free two-point function plus the one-loop two-point function plus a counter term that cancels the divergence at one loop plus higher order terms. Okay. And these higher order terms are going to be of order lambda to the fourth. So these terms here are going to be of order lambda squared. Okay, but if you stare at that one loop diagram for a second, you'll see that, so let's say that we have some momentum p here that's going through here. Then, by momentum conservation, the momentum that's going around the loop, I guess we could call it k, is completely independent of p. So if you compute that one loop contribution, all you get is the free propagator times an overall divergent constant coming from that loop integral. And the point is that divergence is just a constant independent of p. And so it's going to be just completely subtracted off by that counter term. So that means that the leading one loop contribution to the two-point function is trivial once that counter term is taken into account. And so your result will be completely independent of your renormalization scale m. The dependence on the renormalization scale m only enters once you have non-trivial renormalization conditions to impose, to fix, as we'll see in just a second. So what that means is that at one loop, G2 is just given by its free value, which is independent of the renormalization scale m. So that means that, so G2 is just given by its free value, which is independent of m. So that means that at the one loop order, both beta and gamma have to vanish, just by comparing it to the Callan-Zemanzik equation up here. So in particular, beta and the anomalous dimension gamma have to be of order at least one higher order, lambda squared. Okay, so there wasn't too much to do for the two-point function. Let's now consider the four-point function. So what is the four-point function? Well, you have the tree-level four-point function. You have the one-loop contribution to the four-point function. You have actually two other one-loop contributions. So this is the S-channel one. You also have the T and the U-channel ones. And then you have a counter term. I guess it's sort of hard to see there. That's supposed to be a counter term sitting right there. And then you have higher order terms. So what is this a little bit more precisely? Well, the tree level result is just minus I lambda. And then you have this one loop result. So this one loop result is one of the very first things that we computed this semester. I'll just remind you of its answer. So, well, I'll just write it. So I'll pull out a factor of the coupling squared. And then you have three contributions. I'll call them, let's say, m of s plus m of u plus m of t. coming from the S, T, and U channel. And then you have to add in the counter term, delta lambda. And then you have higher order things that appear at order lambda cubed. And ms is given by this loop integral. Well, so if I let this be P1, this be P2, then we have some undetermined momentum K, and a P3 and a P4. Then ms is given by the loop integral, integral d4k over 2 pi to the 4th. Then you have a 1 over k squared coming from this propagator down here, and a 1 over p minus k squared coming from the propagator up here, where p is equal to P1 plus P2. And that is a logarithmically divergent integral. Okay, we know that the fact that it's logarithmically divergent is not an accident. It corresponds to the fact that the coupling lambda is dimensionless. Dimensionless, remember in our power counting discussion of renormalization, dimensionless couplings were associated with logarithmic divergences. And if we computed this using dimensional regularization, I think this is a calculation, I guess in class when we did it using a hard cutoff. We could do it using a hard cutoff. But I think in a problem, we've done dim-reg a million times in this class, so I'll just quote for you the answer. In dimensional regularization, the answer, you get a constant, which is 32 pi squared, an integral dx from 0 to 1, that's the Feynman parameter. Then you have your divergence, 2 over epsilon. Epsilon is d minus 4. And you get plus a constant term, which is not actually going to matter for us, minus the logarithm of x times 1 minus x times p squared. And that constant, well, I'll just write it out for you. You get the Euler-Maccaroni constant and a log of 4 pi. Okay. Plus higher order terms that vanish as epsilon is sent to 0. Okay. And remember, we need to enforce the renormalization condition, which says that G4 is equal to minus I lambda when S is equal to m squared. That fixes the renormalization constant delta lambda. So in particular, it's minus lambda squared, okay, to cancel that lambda squared here, times 3 times, okay, this is where my notation is a little bad. Okay, I forgot I used m for the renormalization scale. So let's not call that m. Let's call it a. You get a 3 times a evaluated at S is minus m squared, at minus m squared. 3 because you have these 3 different contributions here. So that is 3 over 32 pi squared. So you get a 2 over epsilon to cancel this guy. And then from this term here, well, you can just write that as log of x times 1 minus x plus log of p squared. And so you evaluate that at p squared equals to minus m squared, and you get log of m squared. Plus constant terms. So you can see that the entire dependence of G on the renormalization scale m enters through the counter term. So the only way that G depends on the normalization scale is via the counter term delta lambda. And so m d by dm of G4, well, it just comes from this thing here. So the logarithmic derivative just brings down a factor of 2. And there was an overall I out front here. So you get I times 3 over 16 pi squared, because of that factor of 2 coming the logarithmic derivative of log m squared, times lambda squared plus higher order in lambda. And we should compare that to what we expect from the Kalin-Zemanzik equation. So that should be minus beta d by d lambda plus 4 times gamma times G4. And then by comparing those two equations, we can read off the form of the beta function. In particular, what I'd like to do is use the fact, so that's minus beta d by d lambda plus 4 gamma times the 4-point function, which was minus I lambda plus order lambda squared. So I already argued up above using the 2-point function that the anomalous dimension gamma was of order lambda squared. And so you can see that that will give a term here. So you get a gamma times a lambda that's of order lambda cubed. So the anomalous dimension term is only going to be in here. And the beta function has to be such that it reproduces this factor of 3 over 16 pi squared times lambda squared. So if I've done everything correctly, in lambda phi 4 theory, you get a beta function which is 3 over 16 pi squared times lambda squared. Good. And again, that'll be, of course, plus order lambda cubed. Now, I invite you to go and look at the computation we did last week when we studied the Wilsonian effective theory directly by integrating out the UV degrees of freedom and defining the beta function that way. Does anyone remember what we got for the beta function when we did it that way? Nobody remembers. I'll give you a hint. It's the exact same answer. Okay. Just as we found last class. Are there any questions on that? Yes. Yes. Well, yeah, I mean, okay. No, that's sort of an important point. Strictly speaking, as you say, when we introduce dimensional regularization, you do need to introduce another scale. And we should just set that scale to be the scale n. I mean, when I did the computation here, I was a little sloppy, and I didn't introduce that extra scale. Really, you do need to introduce that extra scale because an expression like log m squared makes no sense. Okay, sorry, that was a little messy. An expression like log m squared makes no sense because you can't take the log of a dimensionful quantity. So if we had done this using, say, a hard cutoff instead of dimreg, you would have actually gotten, log of m squared over some dimensionful scale. Okay. So you could imagine introducing some other scale associated with dimreg called mu. And then you would get log of m squared over mu squared. But that's equal to log of m squared plus log of mu squared. Or sorry, minus log of mu squared. So when you take the derivative with respect to m, that mu isn't actually going to enter into the beta function. So I've been sort of sloppy about introducing that additional scale precisely because it doesn't actually matter at the end of the day. But yes, indeed, and indeed, when I wrote down this expression up here, secretly, there's an arbitrary scale you have to introduce, but it's not actually going to enter into any of the final answers at the end of the day. No, that's a good point. Yeah. Okay. That's right. That's right. That's right. When we talked about the different renormalization schemes like MS versus MS bar and so forth, that all depends on whether you decide to cancel that finite piece right there. And the choice of that scale mu is really a choice of the finite part of the delta lambda, the counter term. And as long as you work in terms of only physical variables, your answers are never going to depend on that. It's good. It's an important point, though. I mean, sometimes subtleties like that are important to keep track of. Good. So this is a general lesson, okay? So in general, excuse me. In general, we can always determine the beta functions and the anomalous dimensions by computing correlation functions and looking at excuse me, we can always determine beta and gamma by computing correlation functions and looking at the log divergent piece of the correlation function. Okay. So for example, what we saw here is that if you want to calculate the beta function for a phi to the 4 coupling, you compute the phi to the 4 4-point function, working, say, at one loop order. That has a log divergence. And the beta function was essentially the coefficient of that log divergence. Okay. So the beta function is the coefficient of the log lambda divergence in the 4-point function. So, for example, if you were looking at phi cubed theory in 6 dimensions, that's another case where you have a dimensionless coupling, then the beta function is the coefficient of the log lambda divergence in the 3-point function of the scalar field. And similarly, as you're going to do on your next problem set when you study Yukawa theory, there are 2 beta functions that you're going to compute. One of them is essentially a phi to the 4 coupling like we're doing here, and another of them is a phi psi psi coupling constant, which, as you checked, I think, last week, is dimensionless. And the beta function for that coupling is read off from the log lambda divergent piece of the phi psi psi correlation function. In general, however, you may not be lucky. We were lucky when talking about phi 4 theory that the anomalous dimension vanished at leading order, so that it didn't enter into this computation of the beta function. But in general, and this is something that will happen on the problem set that I just handed out, you're going to need to take into account for the anomalous dimension, which is fixed by a 2-point function. So, for example, next week you're going to study the pseudoscalar Yukawa theory, and determine these anomalous dimensions and beta functions by investigating the appropriate correlation functions and demanding that they solve the Kalin-Zemanzik equation. Okay. Any questions before I continue? So, it's worth stepping back here and thinking a little bit about the big picture. So, we saw that the correlation function, let's say the two-point function of lambda phi 4 theory, obeys a certain differential equation as a function of the renormalization scale. So you enforce your physical conditions at a particular energy scale m, and then once you know these functions beta and gamma, regarded as functions of those couplings lambda, you then have a differential equation that you can solve for your two-point function. And in fact, to the extent that these beta functions and anomalous dimensions are exactly computable, this will give you exact results for the two-point function g. So this gives a very efficient way of computing two-point functions, sort of order by order in perturbation theory. So let's see, how much time do I have? I don't have a ton of time, so I'm not going to bother writing down, I think, the solution of this equation. But I'll just say that this equation can be integrated to find solutions for, say, the two-point function. The two-point function is interesting because if you think about it, in momentum space, the two-point function has to be a function only of p and m. And it had, so the free two-point function is just 1 over p squared. So by dimensional analysis, you must be able to write your two-point function as I over p squared times some function of p squared over m squared. Okay. Has to be p squared by Lorentz invariance, and then if it, by dimensional analysis, it has to be a function only of p squared over m squared. And so you can actually go ahead and plug that back in to this Kalin-Zemanzik equation, and you get a differential equation for this function g. And then, at least implicitly, this differential equation can be solved in terms of beta and gamma. So I don't have that much time left. So I'll just write down the answer. So the general solution of the Kalin-Zemanzik equation says that G2 as a function of P and M okay, I'll just write down the solution. So, well, okay, it's not particularly instructive, so I'm not going to bother writing it down for you. I'll just say that it is obtainable implicitly in terms of beta and gamma. Okay. Because G now just solves some simple first-order differential equation as a function of M. Okay. And you could write down explicitly what that solution is. I'm not sure if it's in your textbook, but I know it's in Peskin and Schroeder, for example. Not sure if it's in the other textbooks. Any question? Yes.
Can you make the constant multiplication as an operator acting on three isotopes?
You want to think about
Yeah, just like
it as a Green's function?
equate the rate with the equation.
Yeah, I mean, sort of. Well, it's more like a heat equation than a Green's function because it's a first-order differential equation rather than a second-order differential equation.
But then that's very different.
Well, so maybe I'm not quite.
If we compare it with the equation of motion, now the dependence of residual, the dependencies are different. Here we have M and F dependence, whereas in the equation of motion we have the K.
Yeah.
But
Maybe I'm not quite sure what.
no, I'm trying to
I mean,
understand how we
So Green's functions are usually useful when you have wave equations, which are second-order differential equation. Here we just have a first-order differential equation, so it's more like a flow equation or heat equation than a wave equation. What's that? It's homogeneous. What's that? Which means, yeah. I mean, if you want, so if you look, I don't know if it's in this in your this textbook, but if you look in Peskin and Schroeder, for example, it's sort of straightforward to at least implicitly write down the solutions to this equation. Okay. So just to summarize, we have seen that in Wilsonian effective theory, you have the beta function which tells you the dependence of the coupling constant on scale. And we have seen that even in renormalized perturbation theory, we still have a coupling that depends on scale. Via an equation, d lambda by d log of scale is equal to beta of lambda. Okay. And we saw that for lambda phi to the fourth theory, this goes like lambda squared, which means that the coupling constant increases with scale. And so we have a Landau pole at some finite value of m. In particular, if you were to graph the beta function as a function of lambda, then it roughly looks like this. What I'd like to do now is just imagine what other sort of possible behaviors you could get for a beta function and what the physical implications would be. So an interesting possibility would be one where the beta function, say, behaved exactly as it did in lambda phi to the fourth theory, except that instead of its first derivative at lambda equals 0 being equal to 0, its first derivative were negative. So for example, if you had a beta of lambda, which looked like this, then your renormalization group flow would look like that. And what would that mean? That would mean that there would be some finite value of the coupling, let's call it lambda star, at which the beta functions vanish. And if the beta function vanishes, that means that suddenly the coupling lambda no longer depends on scale. So let's just write that out a little bit more explicitly. So remember, d lambda by d log m is equal to the beta function. And near the point lambda star, that's just going to be some coefficient times lambda minus lambda star. Okay. Right, just because it's going to be linear. And so we could then go ahead and, so let's call that, yeah, I guess we call it m, that's fine. So then you can go ahead and solve that equation. And it says that when lambda is near lambda star, well, what's the solution of that equation? Well, you could rearrange that, and it says that the integral d lambda over lambda minus lambda star is equal to b times the integral d log m. So it says that lambda goes like a constant, or rather it goes like lambda star plus terms that vanish, I'm just going to call it m, as you take the scale to infinity. Sorry, as you take the scale to 0. So what does that mean? That means that in the infrared, the coupling will flow towards this critical value of the coupling, lambda star, where the beta function vanishes. So you then have the following picture. So let's imagine that we have a very general field theory with random couplings that we don't know very well, describing some very complicated dynamics. But you're only interested in the infrared dynamics of the theory. And that means that you need to study the renormalization group flow into the infrared. And you can see that for certain classes of theories, such as lambda phi to the 4 theory, okay, if you have a term like that in your beta function, what will happen is you'll approach some theory in the infrared, which is not a free quantum field theory because the coupling is non-zero, but rather it's some non-trivial interacting quantum field theory. So, so far in this class, we've imagined studying only free quantum field theories, or theories that are sort of close to free in the sense that you can use a Feynman diagram expansion to study them exactly. But you see that in the space of quantum field theories, there are many more interesting things that can happen than just free quantum field theories. And so in particular, it turns out that indeed there are modifications of phi to the 4 theory where the beta function does have this form. And these lead in the infrared to non-trivial quantum field theories with finite coupling that are inaccessible to standard perturbative Feynman diagram techniques. So in particular, an example of this is phi to the 4 theory in less than 4 dimensions. And the point is that in d is equal to 4 minus epsilon, lambda now is a dimensionful coupling. And so that means that under a normalization group flow, d lambda by d log m is going to be proportional to lambda, rather than lambda squared. So this is something that we saw last class, or maybe the class before, when we started introducing renormalization group flow, where we saw that dimensionful couplings will scale. So another way of saying this is that lambda scales like m to some power. Okay. So I guess I call that power epsilon, or it's effectively d minus 4 here. So what does that, so given that, we expect that in 3 dimensions, there is a non-trivial interacting scalar field theory, which, which is described so there's some non-trivial interacting scalar quantum field theory, which is the fixed point of the renormalization group flow of phi to the 4 theory. So this theory is known as the Wilson-Fisher fixed point. Or the Wilson-Fisher theory. And it's a non-trivial interacting scalar field theory. And there are actual condensed matter systems that appear to be governed by this scalar field theory in the infrared. And so this is what I'm going to discuss next time. And in particular, next time what I'm going to do is I'm going to describe how it is that we can use quantum field theory in order to make predictions for the properties of these condensed matter systems, and in particular for the critical exponents. And then I'll even hopefully have time to present some comparison with experimental data where people have experimentally measured the critical exponents of these various systems and compared them to the expectations based on this Wilson-Fisher fixed point. I think one of the things that is really worth emphasizing here is that, you know, so far in this class, we've talked about only perturbative quantum field theory. So, you know, I think maybe the first problem set or the second problem set I gave you this semester, I probably asked you to, did I ask you to consider a lattice of points and work out the Debye theory? Did I do that? Okay. So, for example, a very simple model of a condensed matter system using quantum field theory is just where you have a lattice of atoms and you study the fluctuations of the atoms, the phonons. Okay. That's essentially a free or weakly interacting quantum field theory. But there's no particular reason why the dynamics of some material should be such that the theory is weakly interacting. And so this renormalization group flow really gives you a language in order to study the space of quantum field theories and to, and what we find is that in the real world there are actual important quantum field theories that are sort of have non-trivial infrared interacting fixed points. So that's what I'm going to try and do next time. Maybe I'll stop here, unless there are any questions. Yeah, no, I don't need one.